Hi apes! Today we're taking a look at Unit 9, Part 1, which is going to focus on how the greenhouse effect works, and then we're going to apply that to global warming. So first off, we do have to have a good understanding of what the greenhouse effect is. Now essentially this definition here, the trapping of heat in the atmosphere, is a good definition of what the greenhouse effect does. So I'm going to show this animation first that has light coming in from the sun. It's absorbed by the earth and transferred into heat. That heat is escaping out of our atmosphere, but some of it is trapped by our atmosphere and reflected back down. So the greenhouse effect is actually a good thing. We don't want all the heat to escape, or else we'd be too cold. So when we have the greenhouse effect in place, it's allowing some heat to be trapped within our atmosphere and allow us to be at a livable temperature. So with the greenhouse gases, we do have some very natural gases like water vapor that act as a heat trapping gas. So what happens as shown here is that outgoing heat will hit these greenhouse gas molecules and it will reflect it back down to the atmosphere, to our lower troposphere. So it's trapping this outgoing heat into our troposphere. Other gases are CO2, CFCs, CH4, N2O, and O3. So CO2 is by far the biggest majority of our greenhouse gases, and where that CO2 comes from primarily is the burning of fossil fuels. Now CH4 is methane. That in itself is a fossil fuel, but one of our bigger impacts here is actually the cow and the meat industry. Because cow farts and burps are heavy on the CH4, and that's actually a tremendous input of methane. N2O comes from the burning of fossil fuels. And CFCs are a coolant or an aerosol. So this is a man-made chemical. This is entirely anthropogenic. That was used a lot in hairspray. Now we don't see CFCs anymore. We do see alternative chemicals, but CFCs have a very, very long lifespan. And so a lot of the ones that were used even in the 70s and 80s are still in our troposphere today, acting as a greenhouse gas. Now what we're going to learn about in a later part of this unit is that CFCs will make their way to our stratosphere and actually cause more problems up there with our ozone layer. But in the troposphere, they do act as a greenhouse gas. So I want to try to draw this out for us so we can kind of get a sense in play of what goes on with our greenhouse effect. So there's our surface of our Earth, and here is our troposphere. So the greenhouse effect does occur in our troposphere. The greenhouse gases are all confined here. And so I've drawn these dashes here to model the presence of the greenhouse gases. So this one might be CO2 and ozone and water, maybe some CFCs, N2O. Okay. So what happens is that wavelengths of energy are coming in from the sun. So we have light energy that's coming in from the sun of a particular wavelength. And the greenhouse gases do not interact with this wavelength of light coming in. Now, as I said, we can't absorb all of the energy from the sun. That would make us too hot. So we reflect some of the energy back. And some of that energy is in the form of heat in a much longer wavelength, and it is allowed to escape our atmosphere. But we don't want all of that heat to escape, because if all the heat were to escape, we would be too cold. So some of this outgoing heat hits these greenhouse gases and is reflected back down. And that keeps us at a livable temperature. So the greenhouse effect by itself is a very good thing to keep our temperature at a very consistent temperature that we can live at. But the problem that we're seeing is we're amplifying the natural greenhouse effect. We are adding CO2 and CFCs and N2O. We are adding a lot of these gases to our atmosphere, and we're blocking up what's known as these atmospheric windows, or this place that heat is allowed to escape. So this outgoing heat, rather than escaping to our outside of our atmosphere, hits a greenhouse gas molecule and is reflected back down. So what we're seeing with global warming is an amplification of this natural greenhouse gas, because we're adding more and more of these greenhouse gases to the atmosphere, and that's where we're seeing the problems start to arise. Now, global warming is often used as an example of a feedback loop. Now, feedback loops are an important concept and sometimes they're a little bit tricky to get. So I want to try to draw this out a little bit down here, that a feedback loop tells us that you have an input of one direction and that leads to an output. Okay? So with a negative feedback loop, your input is an opposite direction of your output, so that an increase of something will lead to a decrease of something, okay? Or you have a decrease that leads to an increase. So your input is in a different direction than your output. A negative feedback loop is not necessarily something bad. So I want to use global warming as an example to teach both negative and positive feedback loops. That if we have an increase in temperature, okay, so our temperature is increasing, in a negative feedback loop, what that would do is the system would respond with a decrease in temperature. So here's some examples of how this occurs in nature. That warming stimulates plant growth. So as the temperature increases, plant growth is stimulated, and plant growth will encourage more photosynthesis, and that decreases our temperature, and our feedback loop stops. Another type of feedback loop is as your temperature increases, you have more water vapor because it's warmer, and water vapor will form clouds that block incoming solar radiation, and that leads to a decrease in temperature, and the feedback loop stops. Now, both of these feedback loops could definitely be in play, but the problem is there's also positive feedback loops in play. Now, with a positive feedback loop, what you see instead is your stimulus and your response are in the same direction, so that here, an increase in temperature leads to a further increase in temperature. And this is where things can get dangerous. That here, if we have an increase in temperature, it makes sense. We already said that that causes evaporation. So more water vapor in the atmosphere means there's more greenhouse gases. So water vapor, not only does it form clouds that could block sunlight, it also may not form clouds and could be water vapor that acts as a greenhouse gas that increases your temperature further. That leads to more evaporation, more greenhouse gases, more temperature. More evaporation, more greenhouse gases, more temperature. The problem here is there's no end point like there was before. Another application of this is that as it gets warmer, the permafrost in our tundra melts, releasing methane, which is a greenhouse gas, which increases the temperature, which causes more melting, which increases more methane, which causes more melting, and it never ends. And then finally, another example is that as it gets warmer, the snowpack in our northern and southern latitudes reduces. So snow, what this does is it has a very high albedo, or reflective quality. So it reflects a lot of sunlight. And so as it warms and our snowpack reduces, we have less sunlight that's reflected, more sunlight that's absorbed, and that increases the temperature, which reduces more snowpack, which increases absorption, which increases temperature, which reduces snowpack, and it keeps on going. So a positive feedback in this case is very hazardous because there's no endpoint, and it continues to go out of control and continues to increase our temperatures. So global warming is a classic example of these feedback loops. Now, both of these feedback loop examples can be in play, both negative and positive. It's just which one is dominant. And it does appear that the positive feedback loops are the dominant loops currently because our global temperatures are increasing. So it is important to understand, though, that the greenhouse effect has been in play for a very, very long time, prior to the Industrial Revolution, prior to humans even being on our planet. So there have to be some natural sources of greenhouse gases. Volcanoes will put out CO2. Methane can come from wetlands from that anaerobic decomposition, as well as the digestion of termites will release methane when they digest wood. N2O can come from the nitrogen cycle, and the water cycle will put out water vapor. So these are the greenhouse gases that put our temperature at the livable way that it is now. But humans have been impacting our greenhouse gases, particularly by burning of fossil fuels. This is responsible for the CO2, the ozone, and the N2O. We also are clearing land and urbanization. This is responsible for more CO2 as well, because the cutting down of the trees prevents the photosynthesis. We have large-scale cattle operations that are increasing our CH4. Rice paddies is one of our major food sources. That as well creates CH4 because of the anaerobic conditions that are set up when we flood those rice fields. And then CFCs, like we said, for coolants and aerosols, is an entirely man-made chemical that acts as a very powerful greenhouse gas. So what we're seeing is that with the increase of all of these greenhouse gases, we are seeing an increase in our temperature. So since 1900, we are seeing an increase in temperature that's going to be magnified as we look out into the future. So these are different scenarios taking into account reduction of these greenhouse gases. Because what we're seeing is an example of global warming. And how I like to think of global warming is that it's an amplification, a magnification of the world's natural greenhouse effect, because we're adding more and more of these greenhouse gases to the atmosphere. Now, what we're most concerned about is CO2. So you can see here the changes in CO2 over the course of the last 50, 60 years or so. So CO2, we do know, has a strong tie to temperature. And you can see that our CO2 has increased. Right now we're at about 413. Now this graph is actually really, really important to see and to understand what it's telling you. One is the overall trend in the increase in CO2. And the second thing is these zigzags up and down, up and down, up and down every year. The CO2 does fluctuate every year, and the reason why it's so regular in its fluctuations is because of photosynthesis. So you see this up and down because in our springtime, the plants are all blooming and into the summer, and so in the spring and the summer, we see a slightly reduction in CO2 because the trees are all blooming and taking CO2 out of the atmosphere. And in the fall and the winter, when our deciduous trees lose their leaves, we see an increase in our CO2. So you see this very regular up and down, but this is a very, very common graph that the College Board likes to use. So it is important to understand why you see these fluctuations in that yearly CO2 level. But the overall trend is that the CO2 is increasing. Now, the reason why we focus on CO2 is because here is our CO2 line, the green and into the blue. And while our temperature does fluctuate, it is difficult to not see the link between an increase in CO2 and an increased trend in our temperature. So if we take another closer look at our CO2 tied to our temperature, going back 400,000 years, you can see that throughout global history, our temperature has fluctuated greatly. We do have interglacial periods, but we also have several glacial periods. These are our ice ages. So our ice ages last much longer than our interglacial periods do. Our interglacials are our warm periods. So we are currently in a very long interglacial period right over here. And you can see that when there are peaks in CO2, there are also peaks in our temperature. So our CO2 peaks do correspond with our interglacial periods, and the drops in CO2 do correspond with our ice age. So this is why there's such a focus on CO2, is because we do have the data that ties CO2 to temperature. And it is difficult to discount that our temperature has been changing ever since the Industrial Revolution. So when we take a look at these different types of graphics, you see historically we were in a little ice age in 1000. This is in the northern hemisphere. And then right around the time of the Industrial Revolution, that's when our temperature increased. This takes a close up at the start of the Industrial Revolution around 1860 and how much that temperature increased. And again here, this is temperatures below our 1950 average, and you can see that here this has been a steady increase in temperature, and that we're seeing more and more of our warmest years ever. So it is hard to deny that our temperature is increasing and that we're in a period of warming on our planet. So we're going to take a closer look at some of the impacts of the global warming in our next lecture. So make sure you leave any questions about how the greenhouse effect works and why we're so concerned about CO2 with this one.